Okay, welcome everyone. So, 我们说风雨无阻，感谢大家风雨无阻的来参加今天的活动。So, we're very happy to have our own Shu-Heng come visit. I think like most of you probably know his credentials and his many of his teachers are here and his classmates. But let me just go over a little bit a summary of his Shu-Heng's history. So he graduated actually here just only 16 years ago in 2010. And he graduated, got his PhD from Harvard at 2016, and spent, I guess, the next 5 years. He has the prestigious long-term fellowship member in an Institute of Advanced Study, and started as assistant professor in Stony Brook in 2021, and recently became an assistant professor at the MIT in 2024. And I think most of you know that he has many honors, and most recently the Breakthrough Prize of 2026 on his work on generalized symmetry. And I guess he'll tell us about generalized symmetry today. So he'll tell us about non-invertible symmetry and what's done and cannot be undone. So let's give a warm welcome to Shu-Heng.
Thank you so much for the nice introduction. Can everyone hear me well? Okay, good. All right, it's a great honor to have the opportunity to give a colloquium here at my alma mater, National Taiwan University. And as Yu-Ting just reminded me how old I am, it's been exactly 20 years since I first enrolled in NTU. So I'm from class B95, if that means anything to you. Now this is also, this colloquium also feels particularly special to me, seeing all these familiar faces in the audience, many of whom I have taken classes from or taken classes with. And today I'll talk about some of the things I've been doing in the past 8 or 9 years. It's some symmetries that cannot be undone. So symmetry plays a foundational role in physics. It helps you simplify complex equations, reduce the number of variables. So for instance, if you are asked to solve the Schrödinger equation for the hydrogen atom, it will be a disaster if you don't make use of the spherical symmetry of the system and insist on working with the Cartesian coordinate, x, y, and z. There's nothing wrong with that, but it will be much more difficult than the spherical coordinate. This is not so much of a joke because I was teaching undergraduate quantum mechanics just the past semester at MIT, and one of the students literally came to my office hour and asked me whether he should use the spherical coordinate or the Cartesian coordinate when solving the Schrödinger equation for the hydrogen atom. Now, symmetry is much more than just a technical tool that helps us solving complex equations. Modern physics taught us that symmetry is also the guiding principle that organizes interactions between elementary particles. This is most nicely summarized in a famous quote by C.N. Yang. He says, "Symmetry dictates interaction." Now, ordinary symmetry transformations are invertible. Now, what does that mean? Let me remind you some of the most familiar examples of symmetries in physics. Mirror reflection is a kind of symmetries that swap the left with the right. Now, if you do it the second time, you swap right with left again, and you go back to where you started. Another familiar symmetry is a rotation symmetry. When you perform a clockwise rotation, you can always undo that by a counterclockwise rotation. This intuition based on Euclid geometry is formalized in quantum mechanics by Wigner's theorem. Wigner's theorem in quantum mechanics states that every symmetry transformation has to be implemented by either a unitary or an anti-unitary operator. Now, a unitary operator has an inverse. U dagger is its own inverse. And together, these unitary operators form a group, the mathematical language describing the ordinary symmetry in physics. Now, in recent years, it has become increasingly clear that this notion of group-like symmetry has become too restrictive the moment we go to quantum field theory and quantum many-body system in general space-time dimensions. A new class of symmetry has drawn a lot of attention. that goes under the name of non-invertible symmetries. As the name suggests, these are symmetry transformations implemented by conserved operators that do not necessarily have an inverse. And under the basic intuition for the non-invertible symmetry, this doesn't hold for the most general type of non-invertible symmetry, but for a large class of them, the basic intuition is that under a non-invertible symmetry transformation, two different states can be mapped to the same single superposition of other states. And the moment you reach the final state, since it can come from either this one or that one, you have forgotten the information of its origin. And therefore, there's no way for you to go back to the initial state. Now, most of you guys in the audience are physicists, and you guys deserve much more than just cartoon. So keep this cartoon in mind. Later, I'll talk about some explicit examples making this more precise. The recent development of non-invertible symmetries really arise from an interdisciplinary collaboration between physicists from high-energy physics, condensed matter theory, quantum information theory, and mathematics. And it has led to many interesting applications, which I will talk about in the rest of the talk. Now, up to this point, you might feel like this sounds like a totally bizarre symmetry transformation. And to find the simplest possible example, maybe you have to go to some very complicated system. Maybe you have to go to 11 dimensions, maybe with 32 supersymmetries, to find the simplest possible examples. Which, by the way, if you do go to 11D with 32 supersymmetries, that will be the low energy limit of the M theory, and that supergravity theory does have interesting non-invertible symmetries. But that's not going to be the topic of the talk today. Today, I'm actually going to start the talk by the simplest possible quantum antibody system, and that's the 1 plus 1D quantum Ising lattice model. So in the next 5 minutes, I'm going to review some basic of the quantum Ising model and introduce the non-invertible symmetry there. There's a close analog of the non-invertible symmetries in the statistical 2D Ising model, but it's much easier to do it for the quantum model. So here's the setup. It's a 1 plus 1D model, so we have our space is one-dimensional, and I'm going to put it on a periodic ring. It consists of L different qubits. Each qubit can be either spin up or spin down, or any linear superposition of these two states. For the rest of the talk, it's safe to assume L to be a finite number. And the Hilbert space for this system is going to be 2 to the L dimensional. And since L can be kept finite, whenever I say operator in the following, it merely means a 2 to the L by 2 to the L matrices. And if you get so bored with the talk, you are even welcome to take out your laptop. You can type everything into Mathematica and check every equation. So that's the space. Now, we're going to work with a quantum Hamiltonian model. And that means the time is going to be continuous. And the time evolution is going to be dictated by a Hamiltonian evolution. The Hamiltonian we're going to start with, but that's not the only Hamiltonian of interest, is the standard Ising Hamiltonian. It consists of two terms. Here, let me remind you, X and Z denotes the poly X and poly Z operators. When you act on a single site, they are just these two 2x2 matrices. Xj means the poly matrix acting on the J site, so and so on. It has two terms. The first term is a sum over X, and the second term is a sum over Z in the nearest neighbor. The second term models the spin-spin interaction, and the first term models a transverse magnetic field. This model has a one-parameter family, which I denote by G. Now, for some of you who come from a quantum field theory background, it will be useful to have a field theory analog of this model. Now, I should emphasize that the field theory analog of this model is not literally the same as the Ising lattice model, but they are in the same universality class. And this is nothing but the famous Landau-Ginzburg model. It's a 1 plus 1 dimensional quantum field theory of a single real scalar field phi. The scalar field has a quartic interaction phi to the fourth and a master. The defining symmetry of the Ising model is a Z2 spin flip symmetry. In the Ising lattice presentation, that's implemented by the following unitary operator, which I denote by V. It's a product of all the poly X. And what it does is that it flips the sign of the poly Z operator, but keeping the sign of the poly X invariant. And as you can see, this Hamiltonian is the simplest possible Hamiltonian you can write down that respects this spin flip symmetry. It's linear in X, but that's fine because X is neutral, and it's quadratic in Z. When you translate this Z2 symmetry to the Landau-Ginzburg model, that's just a symmetry that flips the sign of your scalar field. All right? So far, so good. Now, what does the phase diagram of this model look like? From the Ising lattice model point of view, there's a single parameter G. From the Landau-Ginzburg model point of view, we are going to fix lambda and tune m squared from positive to negative. When G is very large, you focus on the first term. And the ground state corresponds to diagonalizing the first term, which is made out of poly X. And the ground state, more specifically, the ground state corresponds to X having eigenvalue +1 on every spin. That's a state that respects the spin flip symmetry. So that corresponds to a Z symmetry preserving phase. In the field theory point of view, that corresponds to having a positive m squared. And the potential of the scalar fields look like a single well potential. When G is very small, this is the other extreme, you focus on the second term in the Ising lattice Hamiltonian. This time you would like to diagonalize your Hamiltonian with respect to the Z basis. But you have two options. All the Z's can be +1 or -1. In the thermodynamic limit, these two states will have equal energy. And the two states will be exchanged by the spin flip Z2 symmetry, and we're in the symmetry breaking phase. From the field theory point of view, this corresponds to having a negative mass square, and the potential for the scalar field becomes the Higgs potential. And the two vacua corresponds to the two states with poly Z being +1 or poly Z being -1. Since the phases at the two ends of the parameter space are different, that means there has to be a phase transition in between. One can show that the phase transition happens exactly at G equals to 1. And this is a second order phase transition described by the arguably the simplest possible quantum field theory of all, the Ising conformal field theory. Okay. So everything I told you so far, you can find it on Wikipedia. Now the central question we would like to ask in this talk is, if we sit right at the critical point where this parameter G is said to be 1, is there an additional symmetry for the critical Hamiltonian? And by that, I mean in addition to the Ising spin flip symmetry. Now, if you ask this question to someone on the street, the answer you're probably going to get is, duh, of course, there's a Kramers-Wenier transformation that leaves the critical Ising Hamiltonian invariant. In the quantum Ising lattice formulation, the Kramers-Wenier transformation maps the poly X to the product of Z and vice versa. And you can see it with your naked eyes that this critical Hamiltonian, precisely when the coefficient G is said to be 1, is invariant under this Kramers-Wenier transformation. So this all looks innocent and benign. But if you think about it from the Landau-Ginzburg point of view, what the Kramers-Wenier transformation is trying to do is a transformation that flips the sign, not of phi, but of phi squared. Now that feels bizarre. Let me remind you, phi is a real scalar field. To flip the sign of phi squared, you'll be tempted to multiply phi by an imaginary number. But that is not allowed because our scalar field is said to be real. So already from the Landau-Ginzburg point of view, we are start to seeing that the Kramers-Wenier transformation cannot possibly be an ordinary symmetry. So is it really a symmetry at the critical point? Now let's take a look back at the original paper by Kramers and Wenier in 1941. In their abstract, they call this transformation a symmetry property. So even back then, Kramers and Wenier kind of knew that this is not a bona fide symmetry. and they refer to it as a symmetry property. But it's a little bit confusing because I hand you a Hamiltonian, and you find some transformation that leaves the Hamiltonian invariant. What else can you ask for it to be a symmetry? So let's take a look at this transformation again. Suppose the person you ask on the street about the Cramer's one-year transformation turned out to be Wigner himself. Then Wigner would have asked, is this transformation, this Cramer's one-year transformation, implemented by a unitary operator, as the Wigner theorem would have dictated? Now, the answer to that question turns out to be a resounding no. And I'm going to prove that in the rest of this slide. This is going to be the most mathematically intense slide, but I promise you it's only like 3 lines of algebra, so bear with me. We're still early on in the talk, so I hope everyone's still awake. So let's prove it by contradiction. We're going to assume that there was such a unitary transformation, a unitary operator U, that implements the Cramer's one-year transformation. If you open any quantum mechanics textbook, that means, following Wigner's theorem, that this unitary operator U has to obey this equation. When you add U on the operator, say the poly X operator by conjugation, it should give you the right output of the Cramer's one-year transformation. So let's see, given this assumption, where do we land on? Now we can apply this unitary transformation on the defying symmetry of the Ising model, the spin-flip symmetry, which I denoted by V. So V, let me remind you, is a product of all the poly X operators. So this is this definition. But in the next step, I can apply this conjugation operation on each one of the poly X. Following the rule, we assume this transformation turns every single X into a pair of Z. But since we're on a periodic chain, every single Z will appear exactly twice. Poly Z is a 2x2 matrix that squares to 1. And therefore, this whole expression ends up being 1. We're almost there. In the last step, I'm just going to multiply the left-hand side and the right-hand side by U inverse and U. And we land on the conclusion that the spin-flip unitary operator V is a trivial operator. Now that cannot possibly be true. The Ising model is defined by this symmetry. In fact, as we just reviewed, when you tune the parameter G from infinity to 0, you go from a phase transition. When G is small, you are in a symmetry breaking phase, where you have 2 different vacua exchanged by this spin-flip symmetry. So the fact that we arrive at the conclusion that V is an identity operator is a contradiction. And the mistake of the contradiction, and the mistake came from the incorrect assumption that the Cramer's one-year transformation is implemented by a unitary operator. And that concludes the proof. Now, if there's any lesson to be learned from this simple 3-line reasoning, it's that in theoretical physics, we should never write arrow. We're serious people. So we should always write equality. When you write arrow, you don't know what you're talking about. So what is the equation or the equality behind the arrows of the Cramer's one-year transformation? So I'm going to give you the answer without the derivation. There are at least 5 or 6 different derivations of the operator I'm going to present. But I'm just going to give you a flavor of what this operator turned out to be. So I claim the equality behind the Cramer's one-year transformation is encoded in this operator, which I denote by D. So this definition looks a little bit intimidating. It has several different pieces. It's pretty long. It occupies an entire line on the slide. But you don't have to be worried about the details. The first message I want you to take home with is that this is an extremely explicit operator, written in terms of the poly X and poly Z. You can easily write down this 2 to the L by 2 to the L matrix in Mathematica for every value of L. Pick L to be 7. This is just some 2 to the 7 by 2 to the 7 matrix. Now, the second thing I want you to keep in mind is the color of the operator. This operator consists of 3 parts. The first part is a normalization factor, which I shown in gray. And that means I don't want you to pay too much attention to it. Having said that, the gray factors are actually interesting. The square root 2 has to do with the Majorana zero, whereas the 8 in this space has to do with the critical dimension of the superstring theory. But for this talk, I'm not going to say too much about that. The blue part, the only thing I want you to know is that it's a unitary operator, and it's in particular invertible. Why is it unitary? You can actually check that easily in your head. It's a product of a lot of local factors. Each local factor you can check is a unitary operator. How do you check if something is unitary? You just take that operator and multiply it by its dagger and see if it's 1. It takes you probably around 5 seconds to do that calculation. There's a second piece, which is shown in red. Here, V, let me remind you, is the Z2 operators that flip the spin of the Ising model. V can take eigenvalue +1 or -1. And this red operator is a projection operator. And what is a projection operator? A projection operator has eigenvalue +1 in a subspace of your Hilbert space, and it has eigenvalue 0 in the complement. Projection, by definition, is a non-invertible operator. To say it in plain English, is a matrix that has 0 eigenvalue. And since D, the operator, contains this red projection piece, that means the entire operator D is also non-invertible. Nonetheless, I claim D is the hero of the story that lies behind the equality for the Krummers-Wenier transformation. It's straightforward to show that the operator D obeys this formula. This formula looks very similar to the one we had 2 slides ago. The only difference is that this time, I cannot move the factor of D on the right-hand side to the left-hand side because D doesn't have an inverse. And I claim in this sense, the operator D implements the Krummers-Wenier transformation. Even though I cannot move D to the left-hand side, at a critical point, these 2 equations suffice to demonstrate that the operator D commutes with the critical Ising Hamiltonian. And it is therefore a quantity that's conserved under time evolution. And in that sense, it is a symmetry. And this is the simplest example of the non-invertible symmetry. Any question at this point? Right. So you might be a true believer of Wigner theory in quantum mechanics and insist that you don't want to work with this operator D, and you just want to work with its unitary piece, this UKW shown in blue. So what's wrong with this blue operator? The thing with this blue operator is that it almost implements the Krummers-Wenier transformation, except for one site on the entire lattice. It makes a mistake at one site. And because of that, it is not truly a conserved quantity. On the other hand, if you work with D, it implements the Krummers-Wenier transformation everywhere on the closed chain. But the only price you pay is that it is non-invertible. So that's how the non-invertible operator acts on the operator. How does it act on the state? So here I'm using the notation that the upper arrow means that it's an eigenstate of the poly Z operator. The lower arrow means that it's the eigenstate of poly Z operator with -1 eigenvalue. And plus is the eigenstate with, of the poly X with +1 eigenvalue. So these 2 states are precisely the 2 states corresponding to these 2 vacua in the symmetry breaking phase. Starting from either one of them, if you apply the non-invertible transformation, that gives you the disorder state. This state corresponds to the minimum in the symmetry preserving phase. When you apply the non-invertible transformation on the disorder state again, you get a superposition of these 2 states that are exchanged by the Z2 spin flip symmetry. But because this is a 2-to-1 mapping in the first step, that also shows why this operator D is non-invertible. To put it in picture, you should think about the arrow up state as a state where magnetization is pointing upward, whereas the down arrow state corresponds to the magnetization pointing downwards. After you perform the non-invertible transformation, it maps these two states into a different phase. This is the demagnetization phase. This phase is in the same universality class as a magnet on the stove when you heat it up above the Curie temperature. When you apply the transformation again, you get a superposition of these two states, which usually goes under the name of the GHZ state in quantum information theory. So that's all I want to say about the Cramer's one-year non-invertible symmetry in the Ising model. But at this point, you might be thinking, we already know the solution to the Ising model. We don't want to solve the Ising model for the millionth time. So what new things can we learn from the non-invertible symmetry? What is it good for? There are many applications, but I want to single one particular application of the non-invertible symmetries in 1+1 dimension, and that's related to confinement. That's based on this paper by Zohar Komagolsky and collaborators. So in quantum chromodynamics, we can have Wilson lines. You should think about Wilson lines as a probe for very heavy quarks. It's the war line of the very heavy quarks. Now, Wilson lines are considered as the older parameter for confinement and deconfinement phase transition. More precisely, when the Wilson lines are expected to be confined, namely obey the area law, if there are no dynamical quarks in the same representation. Now, the figure here explains why that's the case. So the big Q, the red dot and the blue dot on the two sides, they represent two very heavy quarks. When they're close to each other, there's going to be a flux tube mediated by the gluons, binding them together. But as you try to tear them apart, at certain energy scales, there's going to be a pair creation of the light dynamical quarks in between. And then when they are far separated, they're going to form two bound states at the two sides. When you are in this phase, the flux tube has a tension, and that's why the Wilson lines obeys the area law. Whereas when you go to the long distance limit, they form two separate bound states, and it doesn't cost you extra energy to pull these two bound states further apart. And at that point, they obey the perimeter law. So the usual expectation is that if we do not have such dynamical quarks in the same representation as the Wilson lines, then this mechanism wouldn't happen, and the Wilson lines are expected to be confined. However, this law was observed to be violated in a very famous paper from 30 years ago by David Gross, Plavanov, Mattison, and Snilgum. They considered a toy model for the real-world quantum chromodynamics in 1+1 dimensions. In this model, it's assumed that there are only massless quarks in the adjoint representation. Therefore, when you look at the Wilson lines in the fundamental representation, there's no corresponding dynamical quarks in the same representation. Based on the intuition in the first bullet point, we therefore expect the fundamental Wilson lines in the 1+1 DQCD to be confined. However, explicit calculation seems to suggest that they are deconfined. So what's going on? In this paper by Komagolsky et al., they propose a resolution to this puzzle. They found out that even though in the 1+1 the adjoint QCD there's no dynamical quarks in the fundamental representation, there are actually certain quarks that lives in the twisted sector of certain non-invertible symmetry. And they can be used to screen the Wilson line, causing the fundamental Wilson line to deconfine. And this resolved the puzzle from the 90s. And this is not a special case. There are similar consequences from other kinds of non-invertible symmetry. And their general phenomenon is that there's a large class of non-invertible symmetries in gauge theory that will forbid a trivial confining phase. So this is one application of the non-invertible symmetry that explains certain phenomena that was not understood before. So far we have talked about a lot of examples in 1+1D, and you might be wondering, is there any example in our space-time dimensions, namely 3+1? And that brings us to the many of the developments that happened around year 2021 and 2022. And I'm going to present one of my favorite examples in the quantum field theory that most of you might have learned if you have taken a quantum field theory class, and that's the quantum electrodynamics. So take the ordinary 3+1 dQED that you learned from Pascal and Schroeder. I'm going to assume, take the limit where the electron is massless. If you have taken quantum field theory class, this is the Lagrangian for QED with the electron. Here, psi represents the Dirac spinner for the electron, and F mu is the electric and magnetic field. When the electron mass is ignored, this Lagrangian has a U1 chiral symmetry, which rotates the left-handed electron and the right-handed electron in the opposite way. In equation, this is a transformation that rotates the Dirac spinner by a phase, but with an important factor of gamma 5. This is a transformation that leaves the classical Lagrangian invariant, and therefore seems like a symmetry. Now, at this point, the story should sound a little bit familiar to the story we told in the first part of the talk. In the 1+1D Ising lattice model, when you sit at a critical point, there's a Kramers-Wenier transformation that leaves the Hamiltonian invariant. And here in the 3+1D QED, there is a U1 chiral rotation that leaves the classical Lagrangian invariant. And similar to the 1+1D story, this chiral symmetry was famously known to fail to be a global symmetry quantum mechanically. This is the phenomenon discovered by Adler, Bell, and Jacquet back in 1969. They showed that the classical U1 chiral symmetry upon quantization is broken by the gauge interaction. This phenomenon was hence known as the ABJ anomaly. It was discovered in the context of the neutral pion decay into two photons. It successfully determined the coupling constant between the neutral pion and the electromagnetic field in the pion Lagrangian, and was a huge success in quantum field theory. So this is the story we were told when taking quantum field theory. But if you think about it a little bit, there's something very, very slightly counterintuitive about the story of the ABJ anomaly. Now, usually in physics, we celebrate when we discover a new global symmetry. We use the global symmetry to derive selection rules to constrain the correlation functions. But in the case of the ABJ anomaly, it was exactly the opposite. ABJ anomaly states that it is not a symmetry that one would have naively expected. And just to convince you, I'm not the only one who holds this opinion. This is a logo I found online, which is the logo for the birthday conference of Steve Adler back in 1999. And the title of the conference, I wasn't there, but the title of the conference was called Symmetry Found and Lost. So the final verdict for the chiral symmetry in QED was lost. If it was lost, how come we can derive all these quantitative results from the absence of this chiral symmetry? And wouldn't it be nice if we can reinterpret this classic result from the existence of a more general symmetry rather than the absence thereof? And let me sharpen this question a little bit more. Suppose someone asks you, is chiral symmetry a symmetry in QED? What's the answer you are going to give? Now, when I grew up, I always thought the answer is just no. That's the final verdict of the ABJ anomaly. But when you learn a little bit more, you realize that even though there's not a naive chiral symmetry in QED, there's still something that is conserved in the electron-positron scattering processes. More specifically, the helicity of the electron and positron is always conserved in the scattering amplitudes of QED. Now, at this point, you might be wondering, when you learn quantum field theory, how was this fact explained? Well, let's take a look. This is a screenshot of chapter 5 of Pascal and Schroeder. On this page, they were trying to prove that the helicity has to be conserved, otherwise the scattering amplitude vanishes. you can see that in the way they derive this selection rules, they move the gamma 5 matrix from one end of the trace to the other end of the trace and find the zero. And they wouldn't dare to use chiral symmetry to explain this fact, because they knew down in chapter 19.2, they're going to talk about the ABJ anomaly, where they're going to convince you that the chiral symmetry is actually not the symmetry. So how come there can be a conservation law without the symmetry? And that was the motivation for this paper I wrote with my former student Icho Choi and my former postdoc Hota Len back in 2022. At the same time, there was another paper by our friends Clay Cordova and Kantaro Omori. In this pair of papers, we propose a radical solution to this puzzle. We show that the chiral symmetry is actually not entirely broken by the ABJ anomaly. If you perform a chiral rotation by an angle 2 pi over n, n could be any integer, 13, 7, you name it, then this chiral rotation is actually resurrected as an exact non-invertible global symmetry. The operator in QED for this non-invertible symmetry takes this form. Now, I'm not explaining any of the details for this formula, but the only thing I want you to pay attention to is the color of this operator. It follows the same coloring scheme as in the Ising model. In the Ising model, it has a blue piece and a red piece. The blue piece is an invertible operator which is not conserved, whereas the red piece is a non-invertible operator that is conserved. And together that gives you a non-invertible symmetry. And this symmetry in QED is the underlying reason why the helicity is conserved in QED. This symmetry transformation acts invertibly on the Dirac-Spinner field by a phase rotation in a naive way. The non-invertibility of this symmetry can only be seen when you try to apply this transformation on a very heavy monopole Bohr line. This is a transformation that takes a 'T-Hoof line for the magnetic monopole and turn it into a diode. In the case of the Ising model, the red piece is merely a Z2 projection operator. How about the red piece in this non-invertible symmetry of QED? For those of you who have thought about fractional quantum Hall physics, you should recognize that the action here is precisely the response action for the 2 plus 1D fractional quantum Hall effect with filling fraction 1 over n. So at the level of the slogan, you can say that we use a fractional quantum Hall state to cure the ABJ anomaly. If you think about it, it's kind of interesting. You could have asked, back in 1969, was it possible at all for Adler, Bell, and Jacquet to realize that the chiral symmetry is actually not entirely broken, but becomes a non-invertible symmetry? But that was impossible, because the fractional quantum Hall state was only discovered in 1982. And in this work, we're trying to bring these two very different physics together into one context. There's a similar non-invertible chiral symmetry in quantum chromodynamics below the electron weak scale. This symmetry rotates the up quarks and the down quarks in a particular way. And it provides, and this is an exact symmetry of the QCD in the massless up and down quark limit. In the low energy, QCD is supposed to be described by the pion Lagrangian. So it's natural to ask, how is this non-invertible global symmetry in QCD reproduced by the low energy pion effective Lagrangian? What we show in this paper from 22 is that the coupling between the neutral pion to the electromagnetic field has to take the particular form in order to reproduce this non-invertible symmetry. So at the level of the slogan, you can phrase it as the neutral pion decays because of this non-invertible symmetry in QCD. So this brings me to a fun anecdote I want to tell you all. Back in 2022, when we first realized that there's such a non-invertible symmetry in QED and QCD, we're trying to think about interesting applications for it. And we immediately realized that it has something to do with the neutral pion. But then it occurred to me that for me, the first time I learned the neutral pion decay was when I was taking Professor Zhao Tingwei's quantum field theory class when I was an undergrad. So I immediately went back to my laptop and dug up my undergraduate notes for the final presentation I did in 2010. And this is a screenshot of that note. So you can see that there's a footnote 7 right above the equation where I derived the neutral pion decay rate. And in the footnote I said this transformation is not completely clear to me. And I think this is an interesting lesson that whenever we learn something, we should always document our confusion. Your future self will eventually thank you for that. All right. So that is one application of the non-invertible symmetry in 3+1D. You might be arguing that, okay, this non-invertible symmetry just reproduces something we already knew. Adler, Bell, and Jacquet already derived the neutral pion decay rate back in 1969. Actually, that was one of the first calculations that suggests there should be 3 generations of quarks. What new thing can we learn from the non-invertible symmetry? And that brings me to the second application I want to discuss, which concerns the axion physics. So axion is one of the most promising candidates for dark matter, one of the most popular detection channel for axion is the decay from a single axion to 2 photons, similar to the neutral pion decay to 2 photons. And this is a famous plot that you might see in many of the axion talks, where the vertical axis is the coupling constant between the axion and the photon, and the horizontal axis is the axion mass. The various color regions over here are regions that are excluded by various experiments, whereas this yellow band are 2 very famous models. One of them is known as KSVZ, but today I'm going to focus on the other one by Dine, Fischler, Srinicki, and Zimnisky. It's a very famous axion model, one of the first axion models that goes under the abbreviation of DFSZ. But whenever I look at this diagram, this figure, I always wonder, what is so special about the DFSZ line? Since DFSZ, there are literally thousands or tens of thousands of different axion models that will occupy different regions of this phase diagram. So why, even until the 21st century, we still focus so much on this yellow band dictated by the model of DFSZ? And that was the motivation for a paper I wrote with Hota and Icho, and also with another student from Stony Brook, Matthew Forslund, who's now a PCTS postdoc in Princeton. On the same day, we coordinated our submission with Matt Reeves, who obtained similar results. So in this pair of papers, we provide several different derivations for the following results. One of the derivations used generalized symmetries, and we derive a universal constraints on the axion models under a set of assumptions. I'm not going to spell out all the details of the assumptions. Some of them concerns the global form of the standard model gauge group. But at the end of the day, the statement we make is that any QCD axion model below the DFSZ line must necessarily face the axion domain wall problem in a post-inflationary scenario. Okay, that's a mouthful. Let me translate that into plain English. In plain English, that just means that every point below the DFSZ line is just harder to realize. It doesn't mean that it's impossible, but you will necessarily face some other issue if one day we see an axion models in that part of the phase diagram. And this provides an invariant physical distinction for the DFSZ model in the landscape of axion physics. All right, so I'm close to the end of my talk. Let me summarize some of the key lessons here. The key lessons is that Wigner's theorem for symmetries in quantum mechanics turns out to be too restrictive. The moment we go to quantum field theory and quantum many-body system, symmetries need not be invertible. And there's a close relation between the non-invertible symmetry and the requirement from locality. we talk about two main examples in this talk. The first one is a toy model for fridge magnet, and that's the Ising model. And the other one is the quantum field theory of light and the QED. There are many other quantum systems, both in the continuum and on the lattice, that exhibits non-invertible symmetries. These symmetries identify mistakes in the literature, point to new physical phenomena, and imply non-perturbative constraints on strongly coupled quantum systems, such as the deconfinements in QCD. There are many other applications. Here I'm just making a highly incomplete list of applications in different fields. Now this afternoon I will give a talk around 3:30 on the 8th floor on yet another application of generalized symmetry, where it led to a new exact lattice chiral symmetry in 3+1D. For those of you who are interested, please feel free to stop by. There are applications in quantum field theory and gravity, in condensed matter physics, in quantum information theory, and also in particle phenomenology. For those of you who are interested in learning more about this subject, there are actually a lot of reviews in this field. So yesterday, when I was making the slide, I was trying to make a complete list of all the reviews. And even though I used ChatGPT to help me find all the reviews on this subject, I'm pretty sure I'm still missing a couple of them. So up until now, there are 16 reviews, and I know for sure there are 2 more in the making. And this is really a vibrant field, trying to bridge different subjects, ranging from quantum field theory to condensed matter physics and to mathematical physics. There are also many other collaborations, and most prominently, some of the Simon's collaboration that have overlapped with the research program of generalized symmetries. So this is my final slide, and you guys have been so great sitting here for an entire hour, listening to me about symmetries. But you might take the view that I don't really care. If someone hand me a problem in physics, ask me to solve it, I'm a physicist with a lot of muscles. I'm just going to crack it. I'm just going to shut up and calculate, and I don't care about what symmetries that's available to me. No, that's the totally healthy point of view. In fact, remember the student that came to my office hour asked me if he can use the Cartesian coordinate to solve the Schrödinger equation with the hydrogen atom. If he actually did that, I should by no means applaud to his effort. But if you are some physicist like myself, who is very skinny, who doesn't have a lot of power, then we try to make use of every little trick that is available to us. And I think that's what symmetry means to physicists. It doesn't have to be the only way to solve the problem. It doesn't have to be the first way that people realize to solve the problem. But it's always a tool that's available to us. And I want to conclude the talk by reminding everyone a very famous example of such application of symmetry. And that's, again, the example of the Ising model. So the paper by Kremers and Wannier was written in 1941. And that was 3 years before Lars Ansager's seminal paper on the exact solution for the 2D Ising model. If you read Ansager's paper, he said that Kremers and Wannier's symmetry was very essential for him to derive the final solution for the Ising model. Even though his final solution is completely self-contained, it would not have been possible without the influence of Kremers and Wannier. In the past few years, we have seen many other similar applications of symmetries, admittedly of less magnitude and significance, but I hope that there are more to come in the upcoming years. And with that, I thank you for your attention.
Thank you very much for the nice talk. Any questions?
Thanks for the nice talk. So
I have a question about the paper you mentioned, like Xie Chen's paper on this duality transformation, and you mentioned that she missed one term. And what exactly do you mean? Like, is it possible to get it?
Yeah.
transparent. Thanks.
Yeah, let me go to that slide.
By the way, are you referring to the sequential content gates paper that she's using? That
Correct.
Okay, good. Thanks.
So if you apply the sequential content circuit, this UKW, and you try to conjugate X, so you write UKW, X, UKW inverse, and see what you find on the right-hand side. Now, based on the no-go argument on the previous slide, we know the right-hand side cannot possibly be Z times Z on every single side on the entire chain. What happens is that at one side, exactly which side doesn't really matter. That's a choice. At one side, the right-hand side is not the local operator anymore. It's going to be an operator that has supports on the entire chain. And that's bad. That means the sequential content circuit is not a locality preserving operator. This is to be contrasted with the non-invertible Cramer's one-year operator. When we define the action appropriately, it preserves locality. So in a way, the non-invertibility of the Cramer's one-year symmetry is really a tension between locality and conservation. In quantum mechanics, you don't have a notion of locality, and you can tolerate such a non-local term. But the moment you go to the many-body quantum system, this non-local transformation is bad.
Thank you. Yeah, there's all kind of non-invertible symmetry be written as a unitary operator times a projection operator.
So the question was, can every kind of non-invertible symmetry be written as a unitary operator multiplied by a projection? Now the answer is no. It just turns out that these kinds of examples are particularly easy to introduce.
So what's the additional example?
For instance, in 1 + 1D, you can have, this is a paper from 20 years ago by Alexei Kitaev and collaborators, where they find the so-called Fibonacci symmetry in an anionic chain.
So
That kind of,
like what exactly it will be if it's not written in this form?
it depends on the context. So in the context of anionic chain, it's just a general operator that acts on the Hilbert space. Sometimes it could be a matrix product operator, some other times something more abstract, but the statement is that it need not take this particular form.
Fascinating. Now, if I remember right, a unitary operator has eigenvalues on a unit circle, and a projection operator has eigenvalues that are either 1 or 0, and you multiply two of them. Do you see does this D operator have eigenvalues that are still on the unit circle plus 0, or is it much more complicated?
Okay, so the question is about the eigenvalue of the operator D. So unitary operator with a finite order will have eigenvalue on the circle. But here the operator D actually is, let me restate. Unitary operator with a finite order will have eigenvalue being an nth root of unity. Here the operator D actually mixes with translation. As you can see. If you do it once, you bump it up by half a site. If you do it twice, you translate it by one site. So its eigenvalue will have some kind of Lth root of unity, where L is the number of system size.
But you multiply it by projection operator, meaning your eigenvalues have zeros in them as well.
That's correct. So it could be 0, it could be that Lth root of unity. There's a question about the normalization for root 2. That's a matter of convention.
So is this premise on the symmetry still well-defined in the open chain?
So the question is whether the Cramer's one-year non-invertible symmetry is well-defined on an open chain. That's a great question. You can question me why I started with a closed chain rather than an open chain. The reason is because the Cramer's one-year symmetry involves a lattice translation, and therefore it is necessarily broken by the open chain. Now, this is a special feature of the Cramer's one-year symmetry, and it's not true for more general non-invertible symmetry. So there are other examples where you can perfectly define them on the open chain. The fact that the Cramer's one-year symmetry on the lattice mixes with lattice translation actually has a deep connection with the Nielsen-Inomiya theorem for lattice chiral symmetry.
So my question is, do you have an example of this non-invertible symmetry for the classical system? So for instance, for this 1 plus 1D Ising model, if you use like 2 plus 1D classical Ising, is there something similar?
Yeah. So the question is, all the examples I talk about here are quantum system. Are there examples in classical system? And the answer is yes. I briefly mentioned that. I have a little caveat here, quantum versus StatMech model. So the answer is yes. If you take the 2D classical Ising model, there is a counterpart of the non-invertible coinverse linear operator that I presented. But in the statistical model, you don't usually talk about operator, rather you talk about defect. So these are some modification of your 2D classical Hamiltonian. And conservation in quantum model becomes the topological nature of the defect. So the full statement is that in the 2D classical model, there are non-invertible topological defects.
Hi, very nice talk. So I want to ask is there some development, because when we say the group, well, when you have an invertible symmetry, you can collect it as a set, then you have a group. In terms of this non-invertible symmetry, is that can we collect all the non-invertible symmetry, then we form some weird algebra, then we can do the similar thing as group theory, then we classify all of it and step by step.
Yeah, great question. So the question was, for conventional symmetries, the mathematical language is group theory. What is the corresponding mathematical framework for non-invertible symmetry? So that is the focus, well, one of the focuses of this Simon's collaboration. This is the Simon's collaboration on global categorical symmetry. And the short answer is that the non-invertible symmetries in general dimensions are expected to be described by certain higher fusion category. Now that's quite a loaded word. And to be honest, it has not been completely understood in general space-time dimension. In low dimensions, such as 1 plus 1D, the understanding is pretty complete. And in that case, it's just a fusion category. It still sounds like a scary word, but it's really a very straightforward generalization of conventional groups and their associated anomalies.
Oh, no worries, please go ahead.
Speak loud. In QED, we have chiral anomaly because we choose to preserve the vector gauge symmetry. Does that consideration enter the non-invertible symmetry?
Okay, so the question is that in conventional textbooks and old literature, one usually presents the chiral anomaly, the ABJ anomaly, as a tension between gauge symmetry and the chiral global symmetry. That, as it stands, is not wrong, but I would say that it doesn't make sense to give up on gauge symmetry. Gauge symmetry should really be viewed as a redundancy in the description.
No, I agree.
Yeah.
Gauge symmetry is good to preserve, but I mean, with the consideration of non-invertible symmetry, I mean how that, somehow you have a choice, right? And you should make the smart choice. But with that, do you have some room to maneuver with this?
I would advocate that the modern endeavor on generalized global symmetry is precisely not to think about the alternative route of giving up the gauge symmetry. Gauge symmetry is really something that doesn't make sense to give up on. So the short answer is no.
Okay.
Oh, thank you. I can just speak out loud. That's okay. Thank you so much for the talk. So if I remember correctly, you mentioned that the KW duality actually is an emergent property of the Ising model.
No, it's exact.
It's exact.
Yes, I presented an exact operator that exactly commutes with the critical Ising model. It's not.
Oh, I see. Okay. So is there any other like examples where it's generalized symmetry is emergent? Or,
Okay, so the question is that all the examples I presented here are exact microscopic symmetries. Are there emergent non-invertible symmetries? And the answer is yes. There are many of them. Many of them are emergent. In fact, one of the examples I mentioned here in 1+1 QCD. The papers listed here. They're about the continuum quantum field theory. And it's natural to ask if you regularize quantum chromodynamics on the lattice, for example, using the staggered fermion formalism, can you preserve the non-invertible symmetries of the 1+1 adjoint QCD? And the answer is that they are generally expected to be broken on the lattice, but they become emergent as you go to the continuum limit.
okay. Thank you.
Okay, I think we have a lot of questions, and Shu-Heng will still be around, and as advertised, he has a seminar this afternoon at 3:30. There will be another seminar before, but there's gonna. So anyway, there's two seminars, so Shu-Heng will still be around. So if you have any further questions, you're welcome to stay around. And let's just thank Shu-Heng for now.
Thank you.